Delange's theorem, which states the following. Suppose you have a multiplicative function and it takes values in the unit disk for all n, then we have that our limit, as one more condition is required, if when you sum over the primes, if this is finite, then limit as x goes to infinity of g of n, okay, this is to say the mean value of g is exactly equal to the product over all the primes, and each factor is 1 minus 1 over p into summation nu going from 0 to infinity g of p raised to the nu over p raised to the nu. So, we have built several key steps of the proof. So, let me quickly summarize the key ideas and then we finish the proof today. So, the first idea was from g of n, if you recall, we go to g sub y of n, where y is some fixed number greater than or equal to 2, and what we show is that, so this quantity, by the way, is often denoted as m of g, meaning the mean value of g. So, it is not difficult to show that for any fixed y, m of g sub y is equal to this product, with the stipulation that the primes run only up to y, and you have the same Euler factors as before, 1 minus 1 over p times summation g of p raised to the nu over p raised to the nu. So, this is something that we showed. In fact, what we showed was that as x goes to infinity, what we have is that your summation g sub y of n less than or equal to x is equal to x times this Euler factor plus little o of 1 as x goes to infinity. And now the problem is to be able to remove this y. Okay. So, to do this, we saw last time that by applying exactly the same ideas, you can actually generalize this. So, in this context, let us take g of n, let us exploit the fact that g of n has values lying in the unit disk. So, you can write this as absolute value of g of n times e raised to the I times the argument, where the argument refers to some angle lying between, say, 0 and 2 pi, right. And what we do is, using these angles, we construct an additive function. So, define an additive function theta of n as follows. Theta of n, since it's additive, you need only specify it for prime powers. So, theta of p raised to the nu is just the argument of g of p raised to the nu if this g is not 0. If it is 0, g could take the value 0 for some values, then we define theta to just be equal to 0, and we extend this into an additive function, and given some y let's take, without loss of generality, z to be greater than or equal to y, and let us take y to be at least 2, so that you would have some Euler factors or some prime powers to take into account. Define a of y to be equal to, as we saw last time, summation of all the primes up to y, theta of p over p, and we also extend, we take this and construct another additive function from the above theta, which takes the values which are same as theta if prime lies between y and z and 0 otherwise. So, again, just like we restricted g to g sub y, one can also restrict theta to smaller intervals, intervals for the prime powers, of course. So, this is just theta of p raised to the nu if prime p is strictly greater than y and less than or equal to z, and 0 if not. Now, here so far we have been focusing on the argument, but there is also the absolute value, the modulus of the function. So, we denote that absolute of g of n for any natural number n. Let us denote this by r of n. Okay. So, last time we showed that we have shown that summation n less than or equal to x of our g sub y of n times e raised to the minus I a of y, the perspective of Delange and a lot of other people whose results we will be learning about, is to twist these functions with these exponentials, which makes the analysis very, very neat and an application of techniques we have learned previously. So, we have shown that by extending the same argument as you had for g sub y, you can show that this is equal to x times m of g sub y, where this is that Euler product that I mentioned before, times e raised to the minus I a of y plus little o of 1 as x goes to infinity. What does this mean? What this means is that given some y, you can find a very, very large value of x, so that the difference between this and this is not too big. So, that is, given an epsilon greater than 0, however small, we can find some x naught sufficiently large such that for all x greater than or equal to x0. So, as x becomes very, very large, this difference of these partial sums of g sub y is twisted by these exponentials, okay, minus m of g sub y e raised to the minus this can be made arbitrarily small. Now, what we want to do is, we want to show that these m of g sub y's form a Cauchy sequence. We want to show that the sequence m of g sub y e raised to the minus I a of y, as you take y to be larger values, this is a Cauchy sequence. Once you can show that this is a Cauchy sequence, that it would imply that the sequence converges. Thus, if we can show this, okay, let us call this star, we are yet to prove this, but we are very close to the proof, we will just finish this up today. So, but I want to tell you what it leads to. What this tells you is that your m of g sub y e raised to the minus a of y converges to some finite limit, let us call it m. So, this is m plus little o of 1 as y goes to infinity. And because of what we have written here, in order to show that this is a Cauchy sequence, so what do we need to do? We need to take y and z very, very large, let us say z is greater than or equal to y, and so show that the absolute value of these corresponding differences would be less than epsilon. Using this fact, what we can do is take y and z very, very large, take x to be even larger than those, and show that this particular quantity satisfies the Cauchy condition. Once you can show it for this, the Cauchiness of this part of this absolute value will also follow, and therefore, we will get what we want to do. So, this is the key idea. We want to convert our study of this particular term into these sums. Okay. So, it is sufficient to show that for y and z very, very large, okay, and at least I am going to take it to be at least 2 in order for these the respective Euler products to have some non-trivial terms. So, for large y, z and x, we want to show that the summation this term that we denote as Sxyz, which we define as 1 by x into absolute of the difference between g sub z of n e raised to the minus a of z minus summation n less than or equal to x g sub y of n this can be made arbitrarily small. In fact, what we will show is that as y becomes very, very large, these differences will go to 0 in terms of y. So, last time we did most of the work actually in analyzing our Sx, y, z, and we have shown that this S of x, y, z is less than summation. First, what you have is, so p less than or equal to y, you have 1 minus r of p over p, okay, plus 1 by y is an error contribution coming from all powers p which are greater than or equal to 2, and then you have another term which is what we want to analyze today. So, 1 over x times summation n less than or equal to x, and you have absolute of theta y z of n minus, and since these are all real valued, we can take whole square and this whole thing raised to the half. We derived this inequality with the help of basically elementary properties of complex numbers which lie on the unit circle. But to proceed from here, we have to use some non-trivial things. So, we leave this as it is, and remark that when we started discussing the Delange's theorem, that theorem told you that if the sum of 1 minus real part of g of p over p converges, then that is sufficient for us to derive the mean value. Now, this particular sum has r of p. This is certainly less than this numerator here, since this is the absolute of g of p. This is certainly less than 1 minus real part of g of p. Okay, so this part is taken care of by the conditions given to us in the theorem. It is this part that we want to focus on, and this is an opportune moment to review Turan-Kubilius inequality in the form as we have seen, and then apply it to this additive function theta sub y comma z of n. So, recall. So, we write down the inequality and we break it down into smaller terms of the form that we need. So, let us take f of n to be an additive function. Let us take a of x to be equal to the sum of all those prime powers which are less than or equal to x, f of p raised to the k over p raised to the k. And then let us also take the function d of x to be equal to, again you have sum over all the prime powers up to x, and then you have absolute of f of p raised to the k whole square over p raised to the k, and this whole thing raised to the half. In other words, d of x square is this sum over here. And what we have seen before by the Turan-Kubilius inequality, what we have is that suppose you take 1 by x summation f of n minus a of x whole square, this would be less than where the implied constant can be derived to be an absolute constant. This is less than sum d of x whole square, meaning just this particular sum over here. Now, we want to compare the Turan-Kubilius inequality with the item that we have. You have theta y z of n, which will serve as your additive function, but now you have a of z minus a of y, which seems to be capturing sums here, a part of this sum only for the prime, not for any higher powers of primes. So, in the Turan-Kubilius inequality, we have to separate this a of x and d of x square into two parts. So, what we do is, we write a of x as a sum of two smaller parts of this sum. So, first is the sum corresponding to k equal to 1, okay, f of p over p. And then the next part is running over all the prime powers, which are proper prime powers. So, k is at least 2. So, p raised to the k is less than or equal to x, f of p raised to the k over p raised to the k. And we hope that if our function is suitably, f is suitably well behaved, then the contribution from this part would be very small. Okay, so let's call this a1 of x and let's call this a2 of x. Similarly, we break down d of x whole square into two sums. Let's call this where d1 of x whole square is just the part coming from k equal to 1. So, p less than or equal to x times absolute f of p whole square over p, and d2 of x whole square is all those proper prime powers up to x of So, in terms of these new functions, your Turan-Kubilius inequality is the following. So, we have 1 over x summation n less than or equal to x f of n minus a1 of x minus a2 of x whole square is less than or equal to or less than d1 of x whole square plus d2 of x whole square, right. Now, we have to somehow treat these a2 of x and d2 of x so that they'll become small error terms, and then we can just focus on this part, which is what we need, okay. So, at this stage, what we do is, so by the way, if you want to separate this into, you want to isolate f of n minus a1 of x whole square, you can take this whole square is of the form f of n minus a1 of x whole square plus a2 of x whole square minus 2 times this term times this term, okay. So, that is something we do, and then individually we focus on these smaller parts. So, here's so far what do we have? So, our f is equal to theta yz right. So, what is a1 of x for us? It is equal to summation all those primes up to x theta yz of p over p. But remember, your theta yz of p is capturing the value theta of p provided p lies between y and z and 0 otherwise. So, instead of taking p less than or equal to x, what we actually have is that you have y less than p less than or equal to z theta of p over p, which is a of z minus a of y as we needed. What about a2 of x? This is sum over all the prime powers up to x where k is at least 2, right, and your prime lies between y and z, and then you have theta of p raised to the k over p raised to the k. Now, theta of p raised to the k lies between 0 and 2 pi. It is bounded above by some absolute positive constant. So, this thing a2 of x is certainly less than. First, you go over all those primes lying between y and z, and then k is at least 2. Okay, this is certainly less than. So, we can replace this once you have once you use that theta of p to the k is less than or equal to some absolute constant. You bring that out, you just have 1 over p to the k, and this is certainly bounded above. Although this is a finite sum with p to the k up to x, this is certainly bounded above by 1 over p to the k, okay, where the absolute constant is being taken out here. You already know this is a geometric sum starting from 1 over p square. So, this is of the form 1 over p into p minus 1. So, what you have is summation 1 over p square, where p runs between all primes greater than y and up to z, okay, because p times p minus 1 is it is certainly greater than or equal to some constant times p square. So, though this is not equal to, this is less than, okay, and this is certainly less than 1 over n square, as n runs over all the numbers which are at least y, and therefore, by the integral test you see that this is bounded above by integral of 1 over t square dt, where t is strictly greater than y, and that is of the form O of 1 by y. This is how you take care of the tail of these terms in the Turan-Kubilius inequality coming from higher prime powers. And you can use exactly the same idea for d2 of x whole square. Similarly, is also less than 1 over y. By exactly the same argument, again you have square of something which is absolutely bounded above, and you can follow the same idea. The implied constant of course will be different here. So, what you have is, so in this part, using the fact that a2 of x is O of 1 by y, and d2 of x is also, d2 of x whole square is O of 1 by y, okay, we can isolate what exactly we want. So, from this plus the Turan-Kubilius, you can show that 1 by x into summation n less than or equal to x theta of yz of n minus a1 of x, which in our case is just a of z minus a of y whole square, turns out to be less than 1 over y, okay, plus our summation of y less than p less than or equal to z, theta of p whole square over p, this is d1 of x whole square, and then there is d2 of x whole square also, which we also showed to be O of 1 by y. So, it will all get absorbed in the error term. So, this is what you get, okay, for this part. So, putting all of this together, what we get is thus S x y z turns out to be less than, first you have 1 minus r of p over p, okay, where p is strictly greater than y less than or equal to z, plus O of 1 over y, this part we had already shown in our previous class, plus this part raised to the half, okay. So, you can just write this as square root of 1 over y plus summation p greater than y less than or equal to z theta of p whole square over p, okay. The square is inside. Now, square root of a plus b is certainly O of square root of a plus square root of b. So, you have 1 over square root of y, which is bigger than 1 over y. So, overall what you end up getting is less than summation one minus r of p over p, okay, plus 1 over root y plus square root of the sum as you run over primes between y and z theta of p whole square over p, okay. Now, this is the time when we apply conditions given to us in the theorem. So, we have to look at our, so your g of p, see, you were writing it as absolute g of p, which you denote as r of p, e raised to the I theta of p, okay, where theta lies between 0 and 2 pi, okay. Now, this can also be written as real part of g of p plus the imaginary part of okay, and you can actually derive from elementary complex analysis the following inequalities, which I am going to leave as an exercise for you to think about. 1 minus r of p is less than or equal to 1 minus real part of g of p. Okay. And we also have this theta of p also can be bounded in terms of this quantity. So, turns out that theta of p whole square is less than or equal to pi square times 1 minus real part of g of p. So, this is something that we can exploit and put it in our inequality, which has theta of p whole square inside the square roots. Okay. So, what do we have? This gives us that thus S of S x y z is less than, first let me write this term here, 1 over square root of y. Then you have summation y less than p less than or equal to z of 1 minus real part of g of p over p plus summation. Now you have square root of summation again p going from y to z strictly greater than y. You just told me that theta of p whole square is O of 1 minus real part of g of p. So, again you can, since it all gets absorbed in the O term here, and you have 1 minus real part of g of p over p. Okay. And now this certainly you have p lying between y and z, I can certainly replace it by p greater than y, strictly greater than y. It will just add a bunch of non-negative terms to the thing. So, this inequality will still hold. Now, the condition in Delange's theorem says that this infinite sum, as you run over all the primes, it is a finite sum. If the sum is finite, that means the tail of that infinite series is going to 0 as y goes to infinity. Therefore, it is becoming, for larger and larger values of y, this is becoming very, very small. So, the square root term will certainly dominate this term here. So, this is less than 1 over square root of y plus square root of summation p greater than y 1 minus real part of g of p over p. Okay, as y goes to infinity. So, for very, very large values of y, what you have shown is that this s of x comma y comma z seems to be going to 0. Okay. Let us call this function, instead of writing this term all the time, let us give this function a name. Let us call it eta of y. Okay. So, what have you shown? So, we have s of x y of z is O of eta of y as y goes to infinity, and this term also goes to 0 as y goes to infinity. Okay. S x y of z, okay, was a difference between two sums, and we were looking at it in order to study whether a certain sequence coming from y is a Cauchy sequence or not. Okay. So, notice, by the way, in this error estimate, it does not depend on z at all. So, for any z greater than or equal to y, we have this thing here. So, as long as y is becoming very, very large, this error term is going to 0. So, this gives us that m of, so maybe this we quickly recall that for x very, very large, your absolute of m of g y e raised to the minus I a of y minus m of g sub z e raised to the minus a of z, okay, this is less than your s x y z absolute value plus epsilon. Okay, so for any epsilon you can have an x which is very, very large, so that this holds, and you are saying that this is going to 0, so this can be made arbitrarily small, and therefore what you have is that your this sequence of m of g sub y times e to the minus ay is a Cauchy sequence, and therefore it converges e raised to the minus a of y times m of g sub y, it converges to some finite limit m as y goes to infinity. And if that happens, then, so what is that giving you? So that tells you that, so you've got another thing is that, notice we put z equal to x in the inequality that we obtained for s x y z. Okay, so what we have is this bit over here, absolute 1 over x summation n less than or equal to x g sub x of n e raised to the minus I a of x, okay, minus 1 over x summation n less than or equal to x g sub y of n e raised to the minus a of y. Okay, this can be made very, very small. It's O of eta of y, which goes to 0 as y goes to infinity. Okay, and x is of course greater than or equal to y. So notice now this g sub x of n, it is exactly equal to g of n for all the n up to x, right? So this is the crucial point, because of which we go from our local functions g sub y of n to the global function that we started off with, g of n. So what we combine everything together, and what do we have? So let us take this sum, 1 over x summation n less than or equal to x g sub x of n times e raised to the minus I a of x. Okay, what do we know about this? From our previous considerations, this can be written in terms of m of g sub x and an error term. So this is equal to, this converges to m of g sub y times e raised to the minus I a of y plus O of eta of y, okay, as x goes to infinity. This just follows from this inequality here. So, if you first let x go to infinity, you get this, and now you let y go to infinity as well. Okay. So, what do you get now? As y goes to infinity, this is going to 0. So, this goes to m as y goes to infinity. But what was m? M was the limit of this Cauchy sequence, right? Here. So, you can certainly write it as limit as x goes to infinity, m of g sub x e raised to the minus I a of x. Okay, by just using cleverly a different variable. But what does this eventually tell you? That as x goes to infinity, what do we have? 1 by x summation n running up to x, g sub x of n, which is exactly equal to g of n, since n is at most bounded above by x, minus I a of x is equal to this m of g sub x plus little o of 1 as x goes to infinity. So, what we can now do is, we can, sorry, I forgot, e raised to the minus I a of x plus. So, we can multiply both sides by e raised to the I times a of x, right. So, what will we have? So, you will just be left with m of g sub x here plus little o of 1 times absolute of e to the minus I a of x, which is just 1. So, therefore, from this you can actually just remove these exponential terms. Okay, and this tells you that the mean value of g is this m of g, which we were looking for, and that concludes the proof of Delange's theorem. So, m of g sub x, what was it? This is equal to product p less than or equal to x of 1 minus 1 over p into summation g of p raised to the nu over p raised to the nu. Exactly what you needed to show, that this is the mean value of your function g of n is this. Okay. Okay, now next, in the next couple of lectures, what we are going to do is, we try to use this theorem to study more generally, just we are going to try and minimize the conditions. Okay, we will take for example, what if you have, so next time, what if you just had a multiplicative function with absolute of I am not going to be putting any convergence conditions. If you have functions of this, what can you say about their mean value estimates? Okay, so we are going to say that even though this looks like, very simple, very minimal conditions, they do say a lot of things about the function. Okay, and we will be able to derive mean values estimates with essentially very essential and minimal number of conditions. So, we stop for today.